All right, welcome to Physics Video 7.4. We're going to learn today, finally, about some electricity. We're going to learn about Coulomb's law of electrical forces. The objectives are listed here. They're almost the exact same objectives with gravity. The big difference here is we're dealing with charge instead of mass. So there you go. Kabam! All right, so to learn about electrical forces, we need to talk about what's called charge. All right, so in order to do that, first of all, you got to know what an atom looks like. All right, so an atom is made up of three tiny particles. All right, every atom has a nucleus, and in that nucleus, there are tiny little particles called protons. And those protons have a positive charge of, and you wouldn't know this yet, but we measure charge in what are called coulombs. Down here at the bottom of the screen, it says coulombs. All right. And the charge of a proton happens to be this number here, 1.6 times 10 to the negative 19th coulombs. More important than knowing that number is knowing the fact that it's positive. All right. So inside the nucleus of atom, there's all these protons. So here's 4 little protons in our atom here. All right. So that's one of the 3 particles inside your atom. All right. Also in the nucleus are particles called neutrons. Neutrons actually really are not going to be important at all as we talk about electricity because they don't have any charge. So I'm going to use a little n to represent neutrons. So this might have, 4 or 5 neutrons. They are located in the nucleus of the atom. Okay. Beyond the fact that they're in the nucleus, we really don't care about them at all. If we have any time this year to talk about nuclear physics, then the neutrons will become important. But for now, just know that they're hanging out in there with those protons. All right, and then the final part of an atom is what's called an electron. An electron is much smaller than a proton, but it has a negative charge. I'm actually now questioning if it's smaller. I don't remember the masses off the top of my head. But anyway, it's a very small particle, the important difference is it has the same exact charge as a proton, except it's negative. Okay? And so those sort of orbit around the nucleus. I'm going to kind of oversimplify here and draw it like this. All right? So what's happening is you've got this nucleus at the center of the atom. That's this guy. It's got positive protons in it. And then sort of orbiting around it are these negatively charged electrons that just spin around and around and around. Okay? And it's those charges, the positive and negative charges of electrons that are responsible for what are called electrical forces. All right? Now, it turns out that all atoms have an equal number of electrons and protons. So you're going to have just as many negatives as you do positives. And so what happens is those positives and negatives cancel each other out. So an atom doesn't have any charge. Okay, it's got charges in it, but the positives and negatives cancel out, so there's no sort of what we call net charge. There's no overall charge. All right. However, for reasons that we'll talk about a little bit later in this chapter, sometimes an atom can become what's called ionized. All right. When an atom becomes ionized, what it means is that it's either gained electrons, so it now has more negatives, which would mean it has a negative charge, or it's lost electrons, which means it would now have more positives, so it has a positive charge. And in this case, it's not even called an atom anymore. It's now called an ion. Okay? So when we say that all atoms are neutral, that's a true fact. If you change it and you charge the atom by either gaining or losing electrons, it's no longer called an atom. It's now called an ion, and it's either negative or positive, depending on what happened with the electrons. All right? It is worth noting, and we'll talk about this more later on, barring nuclear circumstances, it's not really possible for an object to gain or lose protons because they're bound up in that nucleus. Okay? So, at this point, really, all you need to know is what's written in blue. Okay? You need to know that electrons are negative, protons are positive, and neutrons have no charge. All right? The rest of this is sort of an intro to stuff that will become more important a little bit later on. Okay? Oh, and also you need to know that charge is measured in what are called coulombs. Okay? Cool. So, Coulomb discovered an equation that calculates the force between 2 charged particles, what's called electric force. But before we get to the equation, how do we know there has to be an electrical force? Well, it's the exact same reason that Newton knew there had to be a force on the moon. You had the moon, right? I'm sorry, you had the Earth, and then the moon. And Newton knew that the moon went in a circle around the Earth. And since it was going in a circle, there had to be a centripetal force pulling it inwards. He discovered that that force was gravity. Okay? So Coulomb has shown us that there's an electrical force between charges. So think about the atom we just drew. The atom we just drew had 4 protons and little electrons floating around the outside, right? And those electrons are, much like the moon orbits the Earth, the electrons are orbiting the nucleus. And the same rationale holds. The electrons want to go in a straight line. There must be a force pulling them inwards. Okay? It turns out that, yes, both the electron and the nucleus have mass. So technically speaking, there is a teeny force of gravity attracting the two. But it's so tiny that it would not be enough to hold an atom together. So there has to be another force. And what we know now is that's an electrical force that prevents those electrons from floating away from the nucleus of the atom. Okay? So, what Coulomb discovered is an equation that relates the amount of electrical force to the two charges and the distance between them. All right? So, here we go. Electrical force works a lot like gravitational force, so much so that scientists are now looking for what they call a unified field theory, or a unified theory. I don't even know that fields are an issue anymore. But anyway, they're looking for one theory that describes the forces between any two objects, because these forces are, in fact, so similar in the way they behave. All right? So here's the main differences. Gravitational force depends on the mass of an object. Okay? Whereas electrical force depends on the charge. All right? The symbol for charge, mass is m, charge is q. Why they chose a q, I do not know. But they did, so deal with it. All right? So, gravitational force depends on mass. More mass means more gravity. Electrical force depends on charge. More charge means more electricity. Okay? The other big difference is this. Gravitational force always attracts two objects. Okay? Electrical force can attract or repel depending on the charges. All right? And it turns out, you know this, opposites attract, right? And then like charges repel. So if you've got, for example, a positive charge and a negative charge, those are oppositely charged, so the electric force is going to cause them to attract towards each other. Okay? Similarly, if you had a negative and a positive, those would also attract, right? Okay? Whereas if you have like charges, if you had either a positive and a positive, those would repel each other. Or if you had a negative and a negative, those would repel each other. Okay? So that's different from gravity, right? With gravity always pulls the two objects together like this. But with electric forces, sometimes they attract, and sometimes they repel. That says repel. All right? So you should know that if they're opposite charges, they point together. If they're like charges, they point apart. Okay? So, it turns out that the electrical force, this slide is exactly the same as the slide that I had for gravity. Dang it. I thought I fixed this. Hold on. Pause. Don't write. Okay. Sorry. I had to correct a typo. So the slide is correct now. Here we go. So electrical force depends on the charge of the two objects. So remember, gravitational force depended on mass 1 and mass 2. Now we're talking about electrical force, which doesn't depend on mass, it depends on charge. And it turns out that the amount of electrical force is directly proportional to the, dang it, charge, I didn't fix all the typos, to the charge of each of the two objects. All right? So before it was double the mass, double the force of gravity. Half the mass, half the force of gravity. Now it's double the charge, gives you double the electrical force. Or whatever, a third of the charge gives you a third of the electrical force. All right? And just like gravity, it also depends on, the electrical force also depends on the distance between the two object centers. Okay? And so the electrical force is inversely proportional to the square of the distance between the object centers. So double the distance gives you a fourth of the electrical force. Okay? A third of the distance gives you 9 times as much electrical force. All right? And remember, the electrical force is the same on both objects. Okay, so if you've got a big charge and a little itty bitty charge, that's supposed to be a minus sign, they're both going to be attracted with the same force. It's just that the bigger charge might move less because it's going to have a bigger mass too. Okay? So what Coulomb discovered is this. The electrical force between two charged objects is equal to K, which is called Coulomb's constant, times the two charges divided by d squared. As a reminder, in the last video, we learned this. The equations are almost identical, except the electrical force depends on the charge, gravitational force depends on the mass. Okay? Also, the constant is different. Okay? So, the problems you're going to be solving are almost identical to the ones we solved last time, except instead of kilograms, we've got coulombs. Otherwise, everything is identical. Okay? So, let's do 2 examples and then call it good for the video. So it says find the electrical force between a 3 times 10 to the negative 17th Coulomb charge and an 8 times 10 to the negative 18th charge if the distance between them is 4 times 10 to the negative 8th meters. See if you can solve this. Pause it right now, write down what you know, do your calculations, and see if you find the electric force. Okay? So there's your given information. This is supposed to be in 18 if you couldn't read that. Coulombs. All right, so now plug your numbers into the equation. So there's what you get if you plug in the numbers, punch that into your calculator, and you should, if you have used your calculator correctly, get an answer of that. Okay, so it's a really small force, but that's because we're talking about tiny, tiny, tiny little charges, okay, on tiny, tiny, tiny little particles. Okay, so next example, we can go backwards. All right, in the last video, we worked and solved the distance in the gravity video. So this time I thought we'd do one where we find the charge, which would be in the other one like finding mass. So pause it, write down what you know, see if you can solve for the charge of the other particle. So there's what we know. Write out your equation and plug in your numbers. Actually, you know what? I am going to do the algebra first and then plug in the numbers. Let's solve this mess for Q2. Multiply both sides by d squared gives you, oh, no, sorry. How about if I actually do what I said? Multiply both sides by d squared gives you this. Now we're trying to get Q2 by itself, so I got to divide by K and Q1. And the answer you end up getting is this. Q2 equals electrical force times distance squared divided by K times Q1. So I am out of room. So I'm going to plug my numbers in now. So here's what we get. So plug in your numbers and you should get this. And then use your algebra to find out the Q is 5 times 10 to the negative 16. All right. So there you go. Video done.